Hey guys, Zong here, back with another math video. Today we're going to be conquering USAJMO, considering AME 1's done. Our school doesn't do AME 2, so we're just going to start JMO prep right now. I didn't do so well on AMC 10, so no point in JMO, but nonetheless, I'll help you guys out. So today we're just going to be doing some number theory, and it's a very hard problem. It's one of those problems where even when you look at the answers on the website, it's really muddled and it's hard to understand. Yeah, so let's just jump right into this. So look at the problem, see if you can solve it. It's alright if you can't. It's a really hard problem. So, alright, so the first thing we notice is that for any number, for any fn, so I should write this fn, the number of combination, like fn, which is fn, for any fn is actually equal to the sum of I equals 0, k to k for f n minus 2I, where 2 to the k is less than n. So what does this mean? So what this means is, for let's say you want to start finding all the combinations of fn. You want to start finding how many possible combinations of 2 to the power of what make fn. So the first case, you probably will decide the first element you want to subtract from n first, and then go from there. So if we say we'll first subtract 2 to the 0, and then see how many combinations there are to get the rest of, to find n minus 2 to the 0. So that's one case. And then another case is that the first element you subtract is 2 to the 1. And then in which case you find all the, it's this part, f to n to the I. In that case you find fn 2 to the 1. How many combinations there are for where your number is subtracted from 2 to the 1, and then 2 to the 2, and 2 to the 3, all the way from 2 to the k is less than n. It just counts all the, this basically just sums up all the number of possible combinations of the numbers where you already have chosen the first element you're going to subtract. So if you choose 2 to the 0 to be the first one you subtract, 2 to the 1, 2 to the 2, it just goes through all the way to 2 to the k, the largest 2, second power that's less than n. So this basically is just this expression is basically the sum of sum of all the combinations for each number in which you've already chosen the first element, and you choose the rest. Yeah, it's kind of mind twisting. We try to understand. Again, this is where you choose the first element first, and you find the combination of that, and then you choose you find a different value for that first element, subtract it from n, and you find the number of combinations in that. So this is just another way of writing it. And in case you haven't figured out, we're gonna use induction. Yes, induction is the way to go on this. And for induction, you usually have to find a identity you want to prove, and that's the really hard part about this. But you probably started out finding out 2 to the 0, 2 to the sorry, not that. You probably didn't start out doing that. You probably started out just going through a bunch of cases, like how many combinations there are for 0, how many are 1, 2, 3, 4, 5. And if you've done that, you've probably noticed a very apparent pattern that for any number n, for any number n that is in the form 2 to the a minus 1, for instance, numbers like 4 minus 1 is 3, so n is 3, 7, 15, those have an odd number of, f of that number is odd. And that gives you a pretty reliable pattern, holds out, and you're probably thinking, wow, I don't need to prove it because I just need to find the answer. Well, I think in JMO you do have to prove your answer. That's the hard part. So you've noticed this pattern. Now how do you solve? How do you prove that for the only numbers that have for fn, for which fn is odd, is in the form 2 to the a minus 1? And really, proof problems, a lot of them, more than 50% of them use induction. So we want to prove that. So the case we want to prove. First, we need a base case, right, for induction. Well, we know f of 0 is I think it's 1. F of 1 is 1, and f of 0 is just 2 to the 1 minus 2 to the 0 minus 1. F of 1 is 2 to the 1 minus 1, and these are both odd. So we already have 2 base cases we can work with. So next we prove that I'm going to draw, to help you guys visualize this, I'm going to draw like a line. So let's pretend this is the center. This is 2 to the a minus 1 minus 1. And this is 2 to the a minus 1. Okay. Let's prove that if all the odd numbers and only the ones that are odd, that are under 2, this is 0, that are under 2 to the a minus 2 to the a minus 1 minus 1, are in the form of 2 to the a minus 1, or I should say 2 to the x, because I don't want to get my variables mixed up, are in the form 2 to the x minus 1. For instance, 2 to the a minus 2 minus 1, 2 to the a minus 3 minus 1, 2 to the a minus 4 minus 1. These are the only numbers for which this function is odd. These are the only ones. So anything in between 2 to the a minus 4 minus 1 and 2 to the a minus 3, this area, there's no number for which fn is even. Only these numbers under this. If these are the only ones that are odd under 2 to the a minus 1 minus 1, then we want to prove that for numbers under 2 to the a minus 1, these numbers are the only ones that are odd. Those are the only ones. Which means that this is what we want to prove. We want to prove this section is all even. Now, why do we want to prove that? Well, think about it this way. Induction sort of works strangely. The mind process is strange. But we already know f0 is 1 and f1 is 1. So all the numbers under f1, or I should say 2 to the 1 minus 1. So all numbers less than 2 to the 1 minus 1, the only ones that are odd are in the form 2 to the 0 minus 1. So that would, like, if you're writing a proof, that would probably help. So for all numbers 2 to the 1 minus 1, or f1, only ones that are odd are in the form 2 to the x minus 1, because the only number under that is f0, and that's in the form 2 to the 1 minus 1, that's odd. So if we prove this identity, if we prove that all the numbers from 2 to the a minus 1 to 2 to the a minus 2 is even, then we can just use the fact that 2 to the 1 minus 1, all the numbers under that are odd. Like all the numbers under that, all the numbers under that are in the form of 2 to the x minus 1 is odd, and thus all the numbers under 2 to the 2 minus 1 include 2 to the 1 minus 1, and all the numbers under that are odd, and thus all the numbers that are under 2 to the 3 minus 1 that are odd are 2 to the 2 minus 1, 2 to the 1 minus 1, 2 to the 0 minus 1. Those are the only ones that are odd, and we can keep going, and eventually this just proves itself. This proves that we can keep this sequence going, and eventually for the only numbers that are odd in the sequence are in the form 2 to the x minus 1, and no other numbers in between that are odd. So how do we prove it? How do we prove that 2 to the a minus, all the numbers from 2 to the, for any number b, which is greater than or equal to 2 to the a minus 1, all the way to 2 to the a minus 2, how do we prove that fb is even? If we prove this, we can prove that the only numbers that we can prove that all these spaces, we can use induction to prove all these spaces, all the numbers in between them are even. FB is even in all these spaces, and thus we can prove the only numbers that give an odd yield are f2 are in the form 2 to the x minus 1. So, oops, dropped my mic there. So how do we go about proving this? It's time for the real juicy part. Okay, so let's say, so we can actually use the first identity right here, Fn equals the summation. We can use this, and we can write Fb equals, and this is one that the part where my proof is sort of different from the proof on USAJMO. I'm not sure if I have it right. They say they replace b with n. It's b minus 2 to the I, but I think it's the same thing if I say they say it's n minus 2 to the I in this expression, but I think it's the same thing if I say b minus 2 to the I. It just makes it easier, more clear. So we want to, so basically b is the sum of all these numbers, right? And we want to prove that b will always be even. All right. So let's do something interesting. So let's say in order for for this sum to be even, there must be an odd number of there must be all even elements, or it must possess an even number of odd elements. So let's find out how many elements in this thing is odd, right? Let's see how many elements in here are odd. So let's find the odd elements for where where Fb minus 2 to the I is odd. If there are an even number of results, if there's an even number of odd numbers in this summation, that means the entire summation is even. Then Fb is even because there's an even number of odd numbers in the summation. We want to prove that for any number in between those two, Fb will always be even, and thus we want to prove that for any number in this range, Fb will always be even. So how do we do this? I'm running out of room. That's not a good thing. It might get messy. So let's see. So let's say we know where the odd numbers are, right? We know where we already know that the odd numbers are 2 to the x minus 1 is odd, right? Well, if we do, so we know f2 to the x minus 1 is odd. So what if we just put in this, b2 to the I? We know that all numbers under 2 to the, we know that b minus 2 to the I has to be in this range. It has to be less than 2 to the a minus 1 minus 1. It has to be under 2 to the a minus 1 minus 1. We already confirmed, we already know the fact that the only numbers under that range, the only numbers that give an odd value are in the form 2 to the x minus 1. So thus, this must be true. This, for sum to b minus 2 to the I, if b minus 2 to the I is 2 to the x minus 1, that means it's odd. That means that means Fb minus 2I. Then Fb minus 2I is odd. And if and only if, because we already confirmed that the only numbers that yield an odd result are in the form 2 to the x minus 1 under the range of 2 to the a minus 1 minus 1. And yeah. So let's see how many of those elements there are. Let's see how many possible elements where this is true. So let me just move this. That means b equals 2 to the x plus 2 to the I minus 1. So how many values of this is true for where b is so what values can this be true for which b is in the range of 2 to the a minus 1 and b is less than 2 to the a minus 1 minus 2? Well, the thing about this is we just need, the only thing we need to prove is that 2 to the x plus and 2 to the I are distinct numbers. And this is important to understand. If 2 to the x and 2 to the I are distinct numbers, then, okay, I'll build on this later. But first, I just want you to know we need to prove they are distinct numbers. So can 2 to the x and 2 to the 1 be the same? If 2 to the x equals 2 to the I and 2 to the x equals 2 to the a minus 1, then this would be 2 to the a minus 1 plus 2 to the a minus 1. We sub these back in here. That would just be 2 to the a minus 1. B equals 2 to the a minus 1. And that's out of range. That's out of this range, so that can't be true, right? Sorry about this. I am running out of room here, so I'll need to make some room. If 2 to the x equals 2 to the I, and 2 to the x equals a minus 2, because we proved that was too much, so what if it's a minus 2? That means b equals a minus 2 plus a minus 2 is just 2 to the a minus 1 minus 1. And that's less than this range. That can't be possible either. That's less than this range. Uh-oh. Which means that, and if one value is less over the range and one value is less than the range, that simply means that x and I are different. Because if they're equal, then if they're both a minus 2, then they're outside the range. If they're a minus 1, if they're a minus 2, they're below the range. If they're a minus 1, they're above the range. And thus, they must be different numbers. And if we know they're different numbers, if 2 to the x does not equal 2 to the I minus 1, then that means for every b minus 2 to the I equals 2 to the x minus 1, there exists a b minus 2 to the x equals 2 to the I minus 1. And why is this so important? It means that if b to minus 2 to the I is in the 2 to the x minus 1, and f2 to the x minus 1 is odd, because we know that from what we're trying to prove, and we know that thus f to the of b minus 2 to the I is odd, and we know so if we know that there's one of these, if we know this is odd, then there's also f b minus 2 to the x is odd. And this is important, because if there's always, for every f to the b minus 2i is odd, and there's also an f b minus 2, there's another matching pair that pairs with it, and that's also odd. That means that for every odd number in this sequence, there's another one. Which means that there's an even number of odd elements in this summation. And if there's an even number of odd elements, so even number of odds, there's an even number of odds in this summation, that means I'm trying to find room. That means this is even. And if this is even, that means for any b which is in this range, if any b in this range, that means that fb has to be even. And we've proven our identity, because if all in this range between a minus 1 minus 1, a minus 1 minus 1, and 2 to the a minus 1, in this range all these numbers are even, that means the only ones that are odd are these. Are odd. And they're the only ones, and we've used induction to prove this identity. But we're not done yet. We're not done yet, because we know that, okay, this range is even, right? This range is definitely even. Okay, so how do we know these are always going to be odd? Are these odd? Well, let's do the same approach that we did with B. I'm going to clear all this out. Getting way too messy. So is 2 to the a minus 1 odd? Well, 2 to the a minus 1, that can be expressed as f 2 to the a minus 1 equals and thus we can do the same thing we did with B, and 2 to the a minus 1 minus 2 to the I must equal in some form 2 to the x minus 1, because those the numbers are odd, so we can cross out the minus 1s, and thus 2 to the I equals 2 to the a 2 to the a equals 2 to the x plus 2 to the I. And what does this mean? The only way this can be true, and this is just this is like common sense. I don't think you actually need to prove this. I mean, the judges aren't that, mean. But the only way this can be true if x is equal to I, and x equal I equal a minus 1. And thus, this proves that the only odd number in this summation, only odd, is 2 to the a f of 2 to the a minus 1 minus 2 to the I. That's the only odd. And that this is because 2 to the a minus 1 minus 2 to the I equals 2 to the a minus 1 minus 2 to the x. So this is the only, since this is only same number, there's only one, there's only odd in here is this element. And if there's only one odd in this summation and all the other numbers are even, that means this is odd. And thus we've proven it. We've proven that the only numbers that can be odd in this, the only numbers which combine that can be odd in this sequence is in the form 2 to the x minus 1. Odd. Alright, we've proven it. We've written a giant paper. Now let's find the answer. So, what's the greatest number that is in the form 2 to the x minus 1 that's over 2013? What's the greatest number? Least number. I mean, let's see. That would be, so 2 to the x would equal 2048. That seems to be the the smallest 2 to the x that's greater than 2013. Minus 1. So it would be 2047, and that's the answer. Really sorry for the really long tutorial. This is a really long problem. But the problems are going to be longer if you have to prove them, right? So I hope you enjoyed the video. I hope you found it interesting. And I'll see you next week. Hey guys, Zong here, back with another math video. Today we're going to be doing AME problem 15 from 2012 AME 2. And yes, it is problem 15, so please don't be ashamed if you can't solve it. I came nowhere close to solving it because I suck at math. So just look at the problem. Make sure you really understand the problem. Try to draw a diagram by yourself. Even the diagram is just hard to draw, so and